So one of the things I hope you've noticed in this last video is a lot of those sort of rules around differentiation end up following through in pretty logical ways when you start to deal with partial derivatives. So we saw, for example, when we calculated what the partial of the temperature with respect to depth was, the product rule applying. I want to sort of follow the chain rule a little bit more with respect to partial derivatives. And to do that, I want to think about an extension of this particular example. So we're again going to be dealing with a temperature, but I'm going to have that, and that temperature depends on what time of year it is, and it also depends on how deep you are, right? And so I'll write that out. So it's A naught e to the minus d over d naught times a sine of omega t minus c times d. Okay. But I now want to think about a slightly different situation, which is I'm going to imagine that I'm engaged in doing a drilling project, and it's a very slow drilling project. And so I'd like to know actually how the temperature is going to be changing as I'm moving into the Earth's surface. So in other words, I'm going to assume that d is actually a function of time, right? i.e. I'm drilling. And I'd like to know how the temperature at my drill location is changing in time. Okay. Now, if you think about that, what I've actually got now is a temperature that depends explicitly on what time of year it is, but that also depends on what time of year it is through the depth that I'm drilling to, which depends on time as well, right? So what I actually would like to do is take a derivative of the temperature with respect to time. Notice that now the temperature really is only a function of a single variable, but I need to take that derivative by considering the fact that temperature depends on time both explicitly through the time and also implicitly through this dependence of depth on time. Okay. Well, so to do that, I'm going to have to use a sort of chain rule kind of approach for that. So let's actually go ahead and do that. One part of this is going to simply be how fast does the temperature change with respect to time explicitly. So I'm actually going to treat d as a constant, and I'm going to now take the derivative of the function with respect to time, assuming that d is constant, right? But the second thing that I'm going to need to do is also ask the question, how fast does the temperature change with respect to depth, and then how fast does the depth change with respect to time? Okay? So temperature is actually going to be changing in time and due to two effects. One effect is the fact that time is passing by, and the other effect is that as time is passing, my location changes. Now you'll note here that we ended up with this sort of second term, which should look kind of familiar from chain rule, right? Because with chain rule, if you've got f of g of t, right? So this is a reminder, remember. If you've got f of g of t and you take the derivative of f with respect to time, right? Well, that's the derivative of f with respect to g times the derivative of g with respect to time, right? So this kind of idea is what leads us to this expression here. And that in general that's sort of generalizable, and this is a sort of generalizable idea, and you can actually see more about this in Stewart. I don't think I'll say any more about it other than to sort of explain this idea that you need to take into account the way that not only the function might depend explicitly on something, but also the way that the function might depend implicitly on something through a dependence in another variable.